Hello students, and welcome to the final video in this lesson. In this lesson, we're going to be going over one more free response question where it's going to be all about position, velocity, acceleration, and distance traveled. Go ahead and grab your calculators for this question, and let's get started. All right, so we're given some information about a plane, and it's flying in a straight line, which is super convenient for our analysis. And that we have velocity given to us in miles per minute for every t minutes. We also know that v is a differentiable function, which might be useful in some cases to know. And so we're given some information in a table here, and we'll be able to answer some of these questions below. So in our first question, it says, find the average acceleration from 5 to 20. We want to make sure that we give correct units. So since we're given velocity, average acceleration is going to equal v of 5 minus v of 20 over 5 minus 20. And I'm not even going to deal with any of these values from the table. I'm not going to try to calculate any of them. All I'm going to do is go, okay, so I'm going to have v of 5, which is 9.2. And we are subtracting minus v of 20, which is 4.5, over 5 minus 20. So let's see what I get out from here. Negative 0.3133. All right, so that's going to equal negative 0.3133. Now we want to make sure that we get the right units of measure. So we have velocity in our numerator, so that's going to be measured in miles per minute. And then in my denominator, I have more minutes. So then that means that our analysis is going to be miles per minute squared. All right, so now in part B, based on the values in the table, on what intervals is the acceleration of the plane? So acceleration, we're given velocity, so we know we're thinking of the derivative of that. Is it going to be guaranteed to equal 0 on the interval from 0 to 40? So we're saying, when is the derivative equal to 0? And to me, that's one theorem that we've learned about, which is Rolle's theorem. So Rolle's theorem says that acceleration will be 0 when we have points on an interval that when we find the average between them, those points are the exact same level. So let's look at these intervals here. And what I notice here in between 25 and 30 is that velocity is the exact same. So somewhere in between there, we know that there is a guaranteed value where the acceleration will be exactly 0 because those y values, the velocity values, will cancel out. So now how are we going to say that? Well, we have to say Rolle's theorem. And we know Rolle's theorem guarantees an acceleration at some time where that's going to be equal to 0. And on the interval that we just looked at, so from 25 to 30, we know that it's guaranteed that acceleration will be 0 somewhere in between 25 and 30 because v of 25 equals v of 30, which is 2.4. So make sure that you specify which theorem you're using, and then we also need to say that it's guaranteed that, restate your question and then say what's the evidence for that. Well, we know it's happening because we filled out the theorem and everything checks out. You might also want to say that the function is continuous and differentiable because it is stated in the prompt above. So now let's look at part C. And it says, does the data represent velocity values of the plane moving away from the point of origin or returning to its point of origin? We really just want to say, okay, why do we make that case? Now, we can't make a concrete case based off of the evidence here. However, we know that the velocity is positive. Every single one of these values is positive. Velocity is positive at 0 all the way across from 0 to 40 minutes. So since we know that velocity is positive, we're trying to make the supposition that direction is never changing. We don't know if any points in between where velocity might be negative, but we can't conclusively say that. What does the trend in the data show us is that since all the values are positive, we know that the plane is always moving in one direction. So it's always moving away from its point of origin. And that's what we're going to write here. All right, and now to our last question. The function f defined by f of t, is given here, and it's used to model the velocity of plane miles per minute from 0 to 40. So looking at this model, what is the acceleration of plane at time t equals 23? So let's label this as part D. And so this is the velocity. And so acceleration at 23 is going to be the derivative of the velocity at 23. And so again, this is a calculator question. So what I'm going to do is I'm going to bring up my calculator and I'm going to make a graph, because that's where it's a little bit easier to work with. And I'm going to put in my function using x for t. So let's go 6 plus cosine of x over 10 plus 3 sine of 7x over 40. All right, so we have that there, and we want to find the acceleration at 23. So I'm going to go menu, analyze graph, and we want that derivative, because this is the velocity function. If we want acceleration, we need the derivative, and we can just type in 23 and hit enter. You can see that it pops up over here. Let me just kind of drag that up, and I get negative 0.40769. Again, 3 decimals is necessary, but 4 is always preferred if you can do it. So I'm going to write down that we got negative 0.408. And what are our units of measure? Well, just like before, we know that this is miles per minute squared. So what does this value indicate about the velocity at t equals 23 minutes? So again, notice that this is a question about velocity and not about speed or whether things are speeding up or slowing down. It's just, what does this say about velocity? Well, what we can say is, since the acceleration at 23 is negative, the velocity is decreasing at a rate of negative 0.408 miles per minute squared. And that is going to conclude this free response question, is going to conclude this 5-video lesson. Of course, if you didn't understand anything given in this video, you want some clarification, please reach out to me. I'm Mr. Hernandez, and this is Mr. Hernandez.